Decibels sound simple. Until they don't. One person says the noise rose by 3 decibels and shrugs. Another hears a faint hum at night and cannot sleep. Today we will decode decibels in a way that helps you read any chart, talk to contractors and neighbors with confidence, and make better decisions at home and at work. Let's start with a truth that makes decibels feel weird. Sound spans an enormous range of pressures. From the faintest whisper we can detect to a rock concert is a difference of millions to one. If we tried to describe that on a normal linear scale, the numbers would be messy and unhelpful. So acousticians use a logarithmic scale called the decibel. Logarithms compress big ratios into smaller numbers that match how our hearing and brain notice change. A practical anchor helps. For sound pressure level, the reference is 20 micropascals. That is a very tiny pressure change around the air in front of you, and it is set as 0 decibels sound pressure level. 0 does not mean no sound. It means the threshold of hearing for a healthy young ear in a lab. When your meter shows 30 decibels in a quiet room, it is 30 above that reference. Here is a second anchor. The famous rules of 3 and 10. An increase of 3 decibels means the acoustic power doubled. It does not mean the sound feels twice as loud. Most people perceive roughly twice the loudness at around a 10 decibel increase. 3 decibels is still meaningful, especially at night or when the sound has tones or rumbles, but it is not a dramatic jump in how it feels. The rules play out in simple ways. Turn on 2 identical, independent machines and you add around 3 decibels compared to 1. 10 similar machines add roughly 10 decibels. That is why a street with many similar sources adds up to a big change even if each one is not that strong alone. If the sources are perfectly in sync, the math changes, but in daily life independence is a good assumption. Now for a point that causes many online arguments. Not all decibels are the same, because we apply different filters and different ways of averaging over time. When someone says it is 60 decibels, the key question is 60 of what exactly? In practice, you need 4 details to understand or compare a number. Which frequency weighting? Which time weighting? Which metric across time? And where the measurement was taken. Frequency weighting first. Our ears do not respond equally to all frequencies. We are much less sensitive to very low frequencies at moderate levels. To mimic human hearing, many measurements use a weighting. When you see dBA, that means the meter filtered the spectrum with a curve that downplays low frequencies and a bit of the very high end. A weighting is common for speech, many environmental studies, and occupational noise metrics. C weighting is flatter in the low frequencies and is good for capturing peaks and bass energy. If you want to check whether low frequency content or impacts are a problem, a C-weighted number tells you more truth than A weighting. Z weighting, sometimes called zero weighting, is essentially flat across the spectrum and is used when you need to analyze sound without a perceptual filter. If you pick the wrong weighting, you can be misled. A rumbling air conditioner might look harmless on a weighting yet be very annoying because the energy sits low in the spectrum. Always ask yourself whether the goal is human perception at moderate levels, low frequency assessment, or raw analysis. Then pick A, C, or Z accordingly. Time weighting next. Real sounds are not steady. To avoid numbers bouncing wildly, meters smooth them over a short window. Fast uses about 1/8 of a second. Slow uses 1 second. Impulse highlights very brief peaks. If you compare a fast reading to a slow reading, you are not comparing the same thing. Match time weightings when you compare, and note them when you report. Now the big one. How we summarize the level across minutes or hours. Think of 3 families. LEC is the energy average over a period. It is like a dose. It tells you the single steady level that would have the same energy as the actual varying sound. Lmax is the highest level reached with the chosen time weighting. And percentiles describe the distribution. L10 is the level exceeded 10% of the time. L90 is the background. L50 is the median. A simple example turns this into intuition. Imagine a bedroom with a quiet baseline of 28 dBA. That is around the L90 at night. Every so often a compressor kicks on and peaks at 65 dBA fast. The average over 15 minutes might be 33 dBA LEC. All three numbers tell a different story. The background tells you how quiet it really is most of the time. The LEC tells you overall exposure. The Lmax tells you why you wake up. Distance changes levels too. Outdoors with a point-like source, doubling your distance reduces level by about 6 decibels. Along a long road, which acts more like a line source, the drop is smaller. Indoors, reflections make the geometry messy and the reduction with distance can be only a few decibels. When you measure or compare, record both the distance and the environment. Let's talk about annoyance and why decibels alone cannot predict it. Two sounds with the same A-weighted level can feel completely different. Tonality, which is the presence of strong narrowband tones, grabs attention. Low-frequency content penetrates walls and travels far, adding a sense of pressure and boom even when a meter downplays it. Intermittency is powerful too. A noise that comes and goes disrupts sleep far more than a steady noise at the same average. This is why a neighbor's humming fan at 45 dBA can be more irritating than a 50 dBA breeze outside the window. The number is not wrong. It is incomplete. When people complain, they are reporting the pattern and the character as much as the arithmetic. How do we measure well enough to make good decisions? Start with a simple checklist. Calibrate your meter with a calibrator before and after the run. Use a windscreen outdoors and even indoors if there is movement of air. Point the microphone according to its specification. Record the model of the meter and the class, the date and time, the weighting, the time weighting, the metric, the duration, the distance to the source, and a short description of the environment. Log enough time to capture patterns. For a home background, 10 to 15 minutes each during the late evening and the early morning is a good start. For an office, separate steady machine noise from intermittent alarms or voices. If you are trying to understand low-frequency issues, capture both A and C weighted values and if possible a short spectrum. What about phone apps? They are excellent educational tools. Some are surprisingly close when used carefully, but they do not replace a calibrated Class 1 or Class 2 meter for regulatory work. Use them to learn and to communicate rough differences. Use proper instruments for compliance or when you want to make decisions that cost real money. Let us revisit the rule of 3 decibels in a practical way. If your project raises the level by 3 decibels, is it always acceptable? Not necessarily. In a quiet bedroom at night, a 3 decibel rise may be enough to move a space from comfortable to noticeable. In a lively restaurant during lunchtime, it may be irrelevant. Context matters. The base level, the time of day, and the content of the sound define the impact. Another small trap is reporting a number without all the qualifiers. 60 decibels could mean a weighted equivalent over an hour, or C weighted maximum with fast time weighting, or a percentile background. These have very different meanings. When you post or share a result, include the weighting, the metric, the time weighting, the duration, the distance, and where you took it. That short sentence turns a mysterious number into a useful one. Here is a miniature case study that many people recognize. You are in a bedroom at night. The average is in the low 30s A-weighted. Every few minutes, the outdoor compressor starts. You feel a low-frequency throb and you wake up. A standard quick check shows a narrow peak near 200 Hz and a handful of smaller peaks at lower frequencies. A C-weighted maximum is far higher than the A-weighted average. The fix is not just to chase 1 more decibel of reduction overall. It may be vibration isolation for the compressor feet, flexible connectors for refrigerant lines, a change in wall or window construction near the most affected band, and duct lining or a different fan speed strategy. When you diagnose the pattern and the spectrum, the correct fix reveals itself. In offices, we see a different pattern. People complain about speech privacy in meeting rooms. Often the sound level is not high, but the spectrum lacks masking and the reverberation time is too long in the speech bands. The measurement numbers tell part of the story, and the room acoustics tell the rest. We will cover room acoustics basics in a future episode, but the message today is this. Numbers need context. Report the numbers and describe the space. Before we recap, a quick note on health and hearing. Prolonged exposure to high levels can damage hearing. If you work around loud sources, use hearing protection and follow your local regulations. For everyday community noise, the goal is not just to avoid damage, it is to protect sleep, concentration, and enjoyment. That is why we care about peaks, tones, and low-frequency energy even when averages appear modest. Let's put everything into a simple mental model you can carry around. Decibels are a logarithmic language for sound pressure level referenced to 20 micropascals. A rise of 3 decibels is a doubling of acoustic power, but only a modest change in how it feels. A rise of around 10 decibels is perceived as roughly twice as loud by many listeners. A weighting mimics our ear at moderate levels. C weighting captures more low frequency and peaks. Z is flat for analysis. Fast means about 1/8 of a second. Slow means a second. Impulse catches sharp transients. Lec is your energy average over time. Lmax is your highest value with a chosen time weighting. L10 and L90 tell you about the distribution and the background. Outdoors, doubling distance tends to reduce a point source by 6 decibels, though lines and reflections complicate that. Indoors, reflections and room modes will often reduce the distance effect. Annoyance is not just about the decibel number. Tones, low-frequency content, and how the sound comes and goes are powerful. That is why 2 sounds at the same weighted level can create very different reactions. When you measure, write down the qualifiers so that your numbers travel well. Weighting, time weighting, metric, time window, distance, and a plain language note about the space. Finally, here is a quick practice you can use this week. Pick one space you care about. Measure for 10 minutes in late evening and again early morning. Log a weighted Lec, L90, and the highest fast maximum. If your meter supports it, also log a C weighted maximum. Note anything you hear that is tonal or intermittent. That 4-line log will tell you more about your environment than a single screenshot ever could. If this episode helped you make sense of decibels, consider subscribing. Next week we will tackle room acoustics fundamentals. Why some rooms sound boomy or harsh. Why speech gets muddy. And 3 fixes that work more often than not. Leave your questions and I will fold them into the Q&A. Thanks for watching and I will see you in the next deep dive.